Hello, everyone. As you may see on the screen, the topic for this talk is kind of ambitious, especially considering that today is the last day of the school, and I definitely don't want to repeat after Sergey and other speakers, because half of the school was devoted to the automated microscopy, automated scanning transmission electron microscopy, and other related to that approach. Rather, I would like to focus on one specific method, one specific approach we are working on, which looks for us quite perspective, quite promising to increase high throughputness of scanning transmission electron microscopy and microscopy in general. However, as an answered topic is quite general, let me start a bit from the broad introduction. And often, let's say, half of my talk, I am starting with this very general slide, where you may see the representation of our pipe dream, or maybe better to say, ultimate goal. So it is a scheme of automated material discovery, where we can represent the whole process as a kind of iterative cycle, where each iteration essentially consists at least of three main stages. It is synthesis stage, characterization stage, and planning stage. So the obvious question, why do we need it? So why do we need this automated material discovery, automated synthesis, except that fact that sitting in front of your laptop and run your transmission electron microscopy or scanning electron microscopy, scanning electron microscopy, scanning probe microscopy manually can be quite boring time to time. So obviously, we would like to find the new materials or optimize materials we have much, much faster than we can do it today. However, if we take this challenge, there are many problems on the way. And the first problem, to observe the first problem, we probably need to look on the process a bit from the different perspective and represent the whole material discovery as kind of time graph, which is started from theoretical explanation or some heuristic search, where we need to define what are the material of interest or what are the promising composition to be synthesized and characterized down the line. Then we need to spend quite a lot of time for experimental discovery and processing optimization. And in the end, as a reward, we move to the manufacturing stage, and we may enjoy because we have new materials or new optimized materials. So what are the problems there? So the first problem is just high dimensionality of space, of compositional space and processing spaces, and we need somehow to navigate through them. So how can we address this problem? So first, we probably want to have models that will help us, that will guide us throughout these high dimensional spaces. And second, the second probably complementary approach is just select more composition, select some area within this space and synthesize it and accelerate the experimental discovery. So we may either choose composition better or accelerate the discovery. Obviously, we would like to use both. We would like to use both of this method to get the maximum gain. Okay, then we meet the main point. To accelerate our experimental discovery, we believe that such microscopy technique as scanning transmission electron microscopy, as atomic force microscopy, are very suitable methods that can at least complement and to some extent substitute the traditional integral characterization discovery. So why so? The first reason, and one of the main reasons, is obviously multimodality. So it is true for scanning transmission electron microscopy and for many other microscopy in general, that by the single experiment, by the single tool, we can get a lot of diverse structural and functional information about our materials, electronic properties, etc. To some extent, scanning transmission electron microscopy, and the same is true for scanning probe electron microscopy, can substitute, or to some extent it's important, our macroscopical characterization as well. So, however, there are multiple problems, or maybe multiple challenges that should be addressed before we reach this point. And the first one, which was one of the main topic of the school, is obviously, so I called it low-level operational human control, but it actually means that we as human control our microscope not fast enough, and the speed how we can reconfigure the electron beam is much, much faster than speed of our average reaction. So what we would like to do, we would like to move, as Sergey presented, from human low-level operation to the situation when we may delegate some routine to either optimization workflow, or probably even move to the situation of hierarchical optimization when we have top-down optimization with LLM agent and other beautiful model or ensembles of models that can run and accelerate our discovery. The second bottleneck is actually a bottleneck of the, to some extent, of the first word It's related that our material characterization still quite complex, and it's require multimodal insight. So even considering that our scanning probe microscopy or scanning transmission electron microscopy provide us a diverse set of various insight, we probably still want to have complementary sources of information, and still only scanning transmission electron microscopy or scanning atomic force microscopy, scanning probe microscopy is not enough for comprehensive characterization. So what we would like, what is our vision, is just organize the whole process, the whole automated experiment, not on the level of some specific modality of some specific level, but rather to move to the point when we can orchestrate the whole process from the whole process centrally. And here I would like, again, probably to pay attention on the asynchroscopy project, which is actually devoted to development of such instrument vendor agnostic abstraction layer, which provide you through the MCP servers the control for the whole facility, for the whole instrument on the level of facility at least, and in the best case scenario even wider. Okay, however, there is a third bottleneck, or maybe bottleneck is third challenge, is not the right definition, which is actually kind of hardware problems. So I would describe it that the system, when we need to change the sample, the hardware that allows us to change the sample, bring us to the point that we always often have one specimen in the column at the time, and changing of our samples goes with some latency, with some time that we need to spend, that we need to devote to this process. So you may argue that there are some commercial systems that allows you to have up to several samples, up to several grids in a row, with automatic changing them in the column, but it is still not enough for high through output characterization, or to meet to follow the rate of high through output synthesis. So one probable solution is kind of hardware-based solution, when we may come up, and we already have in the market such systems that allows us to change samples in automated way. There are another options, another solutions how it can be realized. For example, I found some startups that provide a very wide format objective lenses that can be complemented by multi-orifices wafers, and in this case, you can work with the multiple samples, with the multiple specimens in the row. So There are some solutions on the market, but still the number of specimens, the number of composition is not enough. So how can we, what is the complementary way to solve this problem? The complementary way to solve this problem is probably to reconsider to some extent what is our specimen, what is our sample. And here we can make step aside and look how it is solved, or it was solved for the other microscopy technique and for classical high throughput output synthesis approach. And as you know, the last years, there is a huge advance in high throughput output synthesis. And we today have access to the multiple different ways how we can get more than single composition within the single sample, more than one composition within the single sample. Either it can be a combinatorial growth, when we can realize some compositional or property gradient across the wafer, across the sample. It can be another ways for high throughput output synthesis, such as robotic synthesis or micro pipetting, etc. So if we speak not about scanning transmission electron microscopy, but for the methods which are not required, where we do not have such strict requirement to the sample preparation and the measurement condition, for example, for scanning probe microscopy, such high throughput output samples, such high throughput output synthesis can be naturally integrated into the workflow. For example, in this case, it was metal halide perovskite library consisting of the 96 samples with the different compositions. So we may say that by the single sample, in the single sample, we have access to the 96 different composition, and the characterization of such library can be realized, can be driven in a fully automated approach by the single run with Bayesian optimization or other technique. So by the end of the day, we can characterize the whole library during 1.5 hour, which is compatible with the time that required to for synthesis. So my point, can we somehow to transpose such high throughput output material design, high throughput output synthesis into the scales that are available for scanning transmission electron microscopy and for electron microscopy in general. And there are multiple ways how can you do it. The first is, again, somehow connected to hardware and to the advances in automated FIP. So you can just create a multiple lamellas and put lamellas into the grid. And in this case, you will to some extent replicate the high throughput output synthesis, the combinatorial library, as in case of more traditional synthesis approach. So, sorry, where do we need it? First of all, if we work with such multi-lamella, robotic fabrication of lamellas, it can be pretty useful for correlated investigation. So you have some combinatorial library and you just take lamella for some specific composition and put it together. And in result, you can coordinate, you can coordinate together our, let's say, scanning probe microscopy based characterization and characterization which is based on the transmission electron microscopy. At the same time, we still have access only to a few composition. A number of composition is definitely not enough. So we probably would like to get access to more samples within the single specimen. Moreover, that scanning transmission electron microscopy and the idea of scanning transmission electron microscopy is very high resolution. So the complementary approach how you can solve this problem So probably we need to mention the multiple works of Chad Mirkin group, where they created by actually there are a family of approach. So in this case, they're created by method that is called scanning probe block copolymer lithography, small polymer nanoreactor, which allows you to encode up to several dimensions, create a nanoparticle to encode up to several dimensions. And they showed it in this specific article, how can I do it on the substrate. Probably it was, don't let me wrong, just TEM grid. So on the substrate that suitable for scanning transmission electron microscopy. Additionally, the same group is development of the method which calls kind of partial mega libraries. So the idea that we substitute the single probe by the multi-probe system, it allows us to create mega libraries, so tremendous amount of nanoparticles. And what is important here that we have inside the special encoding. So this is the same idea as in combinatorial libraries. You have special encoding, and due to that, but the density of information is much higher. So they declare that they can create up to 10 million particle library through such polymer pen lithography approach. I should admit that I didn't find some examples when it can be done on the substrate suitable for the scanning transmission electron microscopy, but by the way, it looks like a promising approach. There is another approach, which actually is the main reason why I was so excited to give this talk. And this approach calls random library. So what is a random library? Let's say, smartly speaking, intelligently speaking, random library is combinatorial library without special encoding, which means that you just take everything together and expose it on some substrate, for example, on the stem grid. In this result, you get access to the whole composition, but at the same time, you do not have after exposure, you do not know how it's organized, how it's spatially organized. So the concept of random library and how it can be implemented and integrated was first demonstrated for the automated nano indentation. So, sorry. So the idea is the following: you just make a library. In this case, it was just epoxy resin and some metal particles. And after that, you need somehow to disentangle what are the composition. Hopefully, we have a method like EDS, so you can make EDS mapping. And after that, you have particles and you have map of the composition. And what can you do? You can just navigate through this library, find the composition you need, and make an experiment. And obviously, such exploration can be run with a standard optimization loop, such as Bayesian optimization. And you may try to find some optimal functionality, or you can just run your Bayesian optimization across the compositional space with exploration acquisition function. What we need to account here, what is the difference from the combinatorial library, is actually the cost function. So if you would like to investigate the big sample with nano indentation, probably you need to integrate into your acquisition function some additional function, which is just a cost function. What does it mean? It means that if you take the closest particle to your current position, you don't need to spend time to move your indenter, your probe, too far from the current position, and also in case of random library nano indentation, there is always a problem of alignment. If you move your probe too far, you need then to spend some time to realign your system because there is a disparity. So it will be the error. However, the integration of the cost function is not a big problem. You can just integrate it inside your acquisition function, and after that, this method is fully functional. The second thing, which is quite important, is about compositional mapping. So obviously, EDS mapping has some error, and if you would like to get precise information of composition, you may spend quite a lot of time just gathering such compositional information. So we consider in general two approaches how you can do it. So the first one is you make a fast EDS mapping, and in this case you get a high error for compositional estimation, but you still may complement this fast EDS mapping by clustering just to distinguish different types of the particle and make, let's say, precise or more time-consuming compositional estimation only at the particles or for compositions that are of interest for you. And and the second one is just straightforward approach when you run your EDS mapping with some defined precision to estimate composition and use it as kind of ground truth. Also, the multiple basin optimization approach that allows you to integrate integrate the acquisition type for EDS and balance the error of compositional predictions with the time that you need to spend for that. Okay, small demonstration. Yeah. So how does it work for nano-indenter? So as you may see, the first step is just to align DS map with the field of view of nano-indenter, because field of view of nano-indenter is limited by a few millimeters. And after that, we can run our automated experiment. So the estimated acceleration factor is about 100. Obviously, there is always a question how you calculate this acceleration factor, but nevertheless, such approach is much faster than if you have a number of samples. So, okay. Yes. Can we do the same for scanning transmission electron microscopy? Of course, we can. So, next few slides, it will be kind of dummy model, a bit oversimplified model. So which we use to develop some approach, some method, how we can implement, how we can translate random library discovery into, let's say, more STEM native conditions. So as a first step, we can just estimate what is the accessible dimensionality through such approach. And for that, so it's very naive estimation, low bound estimate, when you may consider your particle as kind of round particles with some size. You may calculate the effective accessible area within the standard grid. It is a bit more than 2.5 square millimeters. And as you may see, the achievable dimensionality of compositional space that can be exposed, that can be theoretically investigated through such random library in STEM is at least 6-7 effective dimension, which is much more than you can even encode into the combinatorial library, into the standard combinatorial library for investigations. And if you would like to translate this approach to scanning transmission electron microscopy, the next specific is that you have access only to the small field of view. So it is exactly the situation that you meet if you try to play some specific computer game when everything except the small field of view is covered by the fog of the war. Obviously, you can make a mapping, but it is time consuming. And what we try to do, we try to get rid of such mapping and rather develop an algorithm which allows you, which enables the investigation within such environment. So why so? Because as you may see, even within a single field of view, you get access to quite a lot of particles, and in many cases, it's much better just to start investigation early rather than make the whole mapping to get particle position. And moreover, when it's much better than try to get all compositional mapping for huge area of the grid search. So how can you do it? This is an overview of the approach we are suggesting. It is running with Bayesian optimization, but actually method is not so important. It can be running with other optimization approach. The idea is the following. You started with some field of view, with some selected region. You definitely make the overview scan to get the position of the particle. You estimate the composition of the particle. After that, you may run your exploration within this field of view with some Bayesian optimization, meaning at the each step you need to define what is the best particle to be measured next to find the optimal composition or to just explore compositional space. It is also important that such investigations somehow combine so the Bayesian optimization is running over the compositional space while we are performing in the real space. So we also need to integrate the cost function. However, within the field of view, the speed, the rate with which you can reconfigure your probe is very, very high. What is interesting? The interesting part is that we actually need at one moment decide that we reach the depletion of the current region and we probably want to move to another one. So the heart of this algorithm is actually how to make this decision. So let's, how to make this decision. So to simulate it, emulate it, probably it's just wrong order. So okay, so how can you make this decision? In general, there are two criteria you need to consider. The first, so there is two intent you need to consider. The first intent, until you have many good unmeasured particles, meaning particles that have a composition far from those that were explored, or they're promising in terms of optimization, you stay within this region. And with ongoing experiment, you will experience kind of depletion, and you will reach the point when only weak or repetitive particles remain. And this is a point when you may consider to take all latency and spend some time to move your field of view, to move your stage, and make another overview scan and get some compositional information. So how can you make this decision based on the, if we do it a bit more parameterized? So in general, you may consider so-called remaining opportunity within the field of view and expected gain if you move to the new region. If we speak about remaining opportunity within the current field of view, so here we have two considerations. First, we may estimate the number of particles we still can explore, that unexplored particles. And second, we may estimate some kind of, we need to estimate some advantage to stay here in terms of acquisition function. Obviously, it can be done in a different way. So for this simulation, we just selected the simplest one and estimated as a maximum of acquisition function for unmeasured particles within this region. The product of these two values can give you the estimate of kind of can allows you to parameterize this remaining opportunity. When we speak about expected gain to move to the next region, actually we are in a bit more interesting or complicated situation, because as you remember, we know nothing about that, which means in turn that we need to make some assumption. So for simulation, we made pretty kind of dummy basic assumption. So we consider that particles are distributed uniformly across the grid, which is obviously not true in a real case. And we also, so it's first of all. And second of all, we consider that composition is also distributed randomly and uniformly across the particles. So we do not consider any clustering, or we do not consider that you may have some inactive region, or for example, you may have some particle aggregation and other effects. So if you know nothing about the region, you have some dummy assumptions. The method that everybody typically use is just Monte Carlo sampling. So what we can do here, so we may make Monte Carlo sampling for the neighboring and other potential region where we can move our stage, which we can consider next. And then with Monte Carlo, we can estimate the expected gain that we probably get if we reach this new region. Obviously, the motion, the changing of the field of view goes with some costs that we need to pay in terms of the time to switch the region and time we need to spend to realign our system. And and actually this is encode our cost of switching. So we in the cost of switching, we encode the fact that we are not able to perform some measurements during this realignment. And the final formula, final criteria to decide whether we should change the region or stay in the current one is pretty simple. We just, it is just difference between our expected gain and cost of switching. And as soon as this difference is above zero, we take a risk and change the region. So now let me move back. So it was kind of general consideration. Then the idea is try to do it on some simulations. So just run model, make some simulations. So we try to do it for the three-dimensional compositional space. As you may see, if we run just several iterations, if we explore just several particles, our exploration is focused within the single field of view. We do not change kind of the global, we do not move the stage, we do not change our field of view. And while we have dense exploration within the real space, in our combinatorial space, we experience kind of random jumps, random transitions. So this experiment was driven by the poor exploration, meaning we would like to reconstruct some imaginary functional dependence across the combinatorial space. What is interesting? So if we use the definition of the problem as we discussed, you may observe several interesting consequences. The first, obviously, when we decided to move our stage, to change our field of view, our model will choose mostly the most neighboring region. It's just a consequences of the uniform distribution and the constant density. The second thing, which is quite interesting, if you look how fast we move from one region to another, what is the remaining part of the particles of the compositions which were accessible within the region, but we did not investigate them, we did not explore them, you may see that this number is decreases within ongoing exploration, which means that our algorithm becomes more and more selective. This actually is a reflection of the fact that with ongoing exploration, there is less and less, let's say, blind spot within our combinatorial space, and meaning that finding, hunting some interesting or promising composition becoming more and more challenging task. The same can be true for the more high-dimensional space as 4-dimensional space and 5-dimensional space. As you may see, we still observe the same dependence. So at the beginning, the percentage, the percent of the measured points is higher than 90%, and more and higher the dimensionality of the investigated space, then high will be the part of the particle we are going to investigate, which actually also reflects the fact that due to the sparse compositional information, typically there is a lower probability that we will have a particle with the same or close composition within the single field of view. But with ongoing experiment, the number of measured particles decreases with time, and our algorithm became more and more selective. You may also see basic metrics, which is mean uncertainty within our compositional space, and the absolute error between because it is a simulation, ground truth distribution and our predicted distribution, which is decreasing with time, and this reflects the kind of standard normal behavior, expected behavior. So the last point I would like to pay attention is regarding the compositional encoding. Yeah, so we need to define the composition, and in case of EDS, it can be time consuming, and sometimes we need to balance. So I already mentioned that to some extent we can combine our EDS with clustering, and we can use some approach for real-time optimization of the time we spending for composition estimation and expected error of this composition estimation. But actually, in case of nanoparticle, we have also additional descriptor, and the simplest one is just a shape. So we may differentiate different types of the particle with a shape, and from this perspective, such method as a deep kernel learning can be of a big interest for investigation. Okay, that's been said. The last slide is actually about some basic demonstration how such method, how such exploration of the random library can be realized in real time. It was done by Utkarsh here in HK. So it is a simplified example, meaning more proof of concept, meaning we did not change the field of view. But the idea is just to run our Bayesian optimization with the novelty as a acquisition function. So the novelty as an acquisition function reflects the situation when we do not trust to our, let's say, surrogate function, and we are hunting, we are trying to find some unexpected, some untrivial behavior we did not observe before. So as you may see, so it's Bayesian-based approach. We are selecting, in this case, not even the particles of cells, but also different region within the single particle and different particle to which looks different for in terms of structure and composition, and trying to trying to investigate it, trying to explore it. Yeah, I think that's pretty it